All right, strap in, everyone. We're going deep today into AI research, the kind that really makes you think about those massive AI models and how they scale.
It's a deep dive, all right, into an AI world where bigger isn't always better. And maybe, just maybe, the real key is the model's architecture.
Exactly. We're talking about a paper called Scaling Laws versus Model Architectures. How does inductive bias influence scaling? And let me tell you, it's packed with insights. The kind that challenge how we think about AI, how we build it, how we train it.
Yeah, this research, it's a real game changer because it moves past that simple idea that more computing power equals better AI automatically, like magic.
Like saying you can win a marathon.
Yeah.
Just by wearing the best shoes. It takes more than that, right?
You got it. This research digs deep into how the structure of the model itself, its architecture, can totally change how it scales and how well it performs in the end.
So size isn't everything, is how that size is, well, organized. What's built into the design.
Yeah, think of it this way. Every AI model starts with assumptions about the data it's going to process. We call this inductive bias, like a model's first guess about how the world works.
Okay, I see where we're going with this.
Yeah.
Different architectures, different biases, and these biases affect how they scale.
Exactly. Researchers tested 10 architectures, seriously tested them, scaling them up. From 15 million parameters to a massive 40 billion, they wanted to know how each one performed as it grew, and if those initial assumptions, those inductive biases, played a part in its success.
So our contenders are transformers, obviously, the superstars of AI right now, plus some interesting variations like evolved transformers and switch transformers. They even threw in some old school convolutional models and those new MLP-Mixers everyone's talking about. It's like a real AI battle royale.
It was a real showdown, and the results, surprising.
All right, you've got me hooked. Spill it. Did the biggest models always win?
That's where things get interesting. Scaling up, not a simple process. Some models, stars at smaller sizes, they struggled as they grew. Others, they seemed average at first, but ended up shining as they scaled.
So what's the secret? What separates the winners from the losers in this scaling game?
That, my friend, is the question. And this research, it dives right into that. It suggests that inductive bias, it's crucial for how a model scales.
Hold on. So you're saying a model's assumptions about data can make or break its ability to handle massive amounts of information.
That's what it looks like. And that changes everything for how we design and develop AI going forward. Think about it like this. If a model starts with assumptions that are too narrow, it might hit a wall in how much it can learn, even with tons of data. But if its assumptions are too broad, well, then it might miss the important patterns lost in all that noise.
That makes sense. It's like finding that sweet spot. Not too narrow, not too broad, just right for scaling up.
You got it. And here's the kicker. The just right approach. Might not be obvious at first. This research, it found something really interesting. The vanilla transformer, the basic one, it consistently showed some of the best scaling.
Wait, really? The vanilla transformer? I always thought those were, well, kind of basic. Not exactly pushing the boundaries of AI.
Right. It's kind of an underdog story. But think about it. This might mean that the vanilla transformer, its assumptions, its bias, even if it seems simple, it's really good at picking up patterns in data, even as the data gets bigger and bigger.
So maybe it's not about being super fancy or complex, but having the right starting assumptions built in.
Right.
From the beginning.
Exactly. And this research, it went further. They didn't just look at how well these models scaled up. They also looked at how they use that knowledge on specific tasks, what researchers call downstream performance.
Right, because memorizing a whole encyclopedia, that's one thing.
Yeah.
But actually using that knowledge to solve problems, to answer questions, that's a whole different ballgame.
You got it. And that's where things get even more interesting. Some models, they aced the memorization test, what researchers call upstream performance. But then, when it came to actually using that knowledge in a real-world setting, they struggled.
Like they crammed for the exam, but couldn't apply the information in real life.
Perfect analogy. This all points back to inductive bias. Some architectures, they're great at soaking up information, but they're not as good at applying it flexibly in a way that makes sense in different situations.
So we know now that inductive bias is key for scaling up effectively. But this research looked at 10 different architectures, each with its own unique bias. Any standouts, any big wins or failures?
Oh, absolutely. Let's talk about a couple. First up, linear time attention models. Like Performer, they're designed for efficiency, for speed. Sounds good, all right?
Yeah, faster AI. Who would want that?
Well, here's the thing. When they scaled Performer up, it ran into some problems. Turns out faster isn't always better when you're scaling up.
It's like you can't have it all. You get speed, but you might lose out on scalability. Are there other trade-offs like that, things we need to watch out for?
Definitely. Look at the MLP-Mixers. They were promising at first, but then as they scaled, problems popped up. Makes you wonder, is their architecture, even though it's new and innovative, is it really right for handling these massive data sets?
I'm seeing a pattern here. More computing power isn't always the answer. It's about finding the right balance between efficiency, performance, and scalability. And it sounds like inductive bias is key to that balance.
It is, and this changes the game. For AI development, it means we need to be much more careful, more thoughtful about the architectures we choose, especially as we build more powerful, more complex AI systems.
Like we're at this turning point
Yeah.
in AI, where it's not just about bigger models, it's about smarter ones. Models designed to scale, to adapt, maybe even learn a bit more like we do.
Yeah, I think you're right. This research opens up so many possibilities. Imagine AI that can handle tons of data, but also use that data to solve new problems it's never seen before. AI that learns constantly, adapts as the world changes. AI that reasons, makes decisions, more like we do.
It's almost like a whole new kind of intelligence, not just brute force number crunching, but something deeper, more sophisticated.
Exactly. That's what's so exciting about this. It's not just small steps forward. It's a totally new way of thinking about AI, what it can do.
Now, you mentioned earlier some models had trouble scaling. Any architectures that really surprised you? With the limitations, I mean.
One thing that stood out, the problems with scaling up linear time attention models, like Performer, they were designed to be more efficient, with the whole attention mechanism thing. But it seems like those benefits, they don't always scale up smoothly.
So it's that trade-off again. You want speed, you want efficiency, but you might sacrifice scalability. And maybe that trade-off gets even bigger as we deal with more and more data, more complex problems.
Exactly. It shows how important it is to think long-term. When you're choosing an architecture, you can't just go for those quick wins. You need to consider how these models will behave as they grow, as they change.
It's like designing a city. You can't just build skyscrapers without thinking about the infrastructure, the transportation, how sustainable it all is.
Perfect analogy. It shows how we need to think about AI holistically. Think about the entire life cycle of the model, from design to how it's used, to eventually taking it offline.
So it's bigger than just scaling up what we have now. It's about inspiring a new generation of AI architects, researchers, developers to think differently, to question what they know, to push the limits of what AI can do.
Absolutely. And that idea, it goes beyond just the technical stuff. It's about adapting, learning continuously, always trying to understand the deeper principles, the things that make complex systems tick.
This deep dive has given us a lot to think about. Inductive bias, the vanilla transformer, who knew? We really got into the nitty-gritty of AI scaling. But before we go, I have one last thought. We talked a lot about the technical side, but there's a deeper question here, I think.
What's that?
As we create AI, more powerful, more sophisticated, AI that learns, adapts, even reasons, almost like us, what does it mean to be human in a world with these intelligent machines?
That's a big question, and it's one we'll all be asking ourselves. In the years to come, I don't have all the answers. But I do believe that by understanding AI, its strengths, its limitations, by having these conversations, we can make sure that AI, these powerful tools, are used to make our lives better, to help us reach our full potential.
That's a great note to end on. And with that, we've reached the end of our deep dive into the world of AI scaling. But the conversation doesn't stop here. Keep exploring, keep asking questions, keep pushing the boundaries, and be a part of shaping the future of AI.